So we'll tackle section 4.7 now, integration by substitution. And this will take us through about the first 8 examples, some of which we'll do together on this video and some of which you'll do on your own. And we'll talk about the rest of the notes as we get back into class. But some of these things are doable, kind of like just a little bit of guidance. Start with the warm-up, okay? The warm-up is something that you kind of know how to do, but just in case you're feeling a little bit kind of iffy about it, let me just remind you that 2 is a constant and can be treated like a constant. So in other words, we could take it out of the integral, and that kind of reveals to us the answer a little bit more, right? The integral of 1 over x is ln of the absolute value. So here, our final answer is just 2 ln of the absolute value of x, of course, plus c. So as we go through the rest of these examples, you'll see the definition of, the integration of the natural log, and we kind of touched on it just a tad bit, but now we get into a little bit more complex examples. So if we were to go to the next example, example 1 here, I want to show you why it's not as simple as maybe it might look. So for instance, if your answer was ln of 5x plus 2, right, and you think to yourself, oh, that's got to be right. Well, let's go backwards, right? The derivative of that is 1 over 5x plus 2. So you say to yourself, okay, great, that's exactly what I have, but not so fast, because remember, there's a chain rule involved. So 1 over 5x plus 2 times 5, right? So where is that 5 going to come into play? Well, here's the deal. We're going to now approach this with the same idea that we had previously with some of the substitution integration we talked about. So we looked at power functions, exponential functions, and trig functions. Well, we never looked at rational functions, right? And so it's natural then in those cases to look to the denominator for u. So we're going to make u equal 5x plus 2, which means du is equal to 5 dx. And so we've seen a couple examples now where we kind of know how to handle this a little bit better. We're off by a 5. So we would replace that 5 with a 1/5 outside the integral. And then we put it into this form right here, 1 over u du, or du over u, giving us 1/5 ln of the absolute value of u plus c. So as my final answer, of course, we go back and we make that substitution for u. And so here's what we arrive at. 1/5 ln of the absolute value of 5x plus 2 plus c. So this is kind of quick, but that's really it. We're looking for the correct u choice, right? And just kind of divert your attention over here for a second. Had it been 5x plus 2 to the 7th power, then if u is 5x plus 2, du would be 5, and we'd be doing this the same exact way. We'd be doing 1/5 integral u to the 7th, and we'd be going from there. So it's really just where we focus our eyes. So keep that in mind as we go through some of these examples. Let's try another one. So example 2, right? You might even be ahead of me at this point, but we're going to let u equal the denominator, 3 minus x cubed. Why? Because I'm noticing that the derivative of that is negative 3x squared, which means, if I kind of look carefully, I have the x squared and the dx. I just don't have the negative 3, right? So I'm off by a negative 1/3, right? So we'll compensate for that as a constant outside the integral, and there we are, right back into the 1 over u format. So that's your job, really, is to try to get these into that 1 over u format so that you can integrate them rather easily, right? ln of the absolute value of u. So that's always what we're looking for. So final answer here, negative 1/3 ln the absolute value of 3 minus x cubed plus c. I'm going to jump a little bit. Let's go to example 5. Okay, you can do 3 and 4 on your own, and after this slide, actually, we'll get you the answers to those. But let's look at example 5. So if we see, if this one's a little bit more loaded looking because there's a lot of stuff going on here, but if we approach this with the same mentality, and let's say we didn't know what to choose for u, you have a kind of a world of problems here. If you choose the numerator for u, yes, the derivative involves some sign of 2x and some form of that, but that's it. The derivative of 3 is 0, so this x wouldn't be appearing anywhere. So let's just make a note that the numerator is not u. We're going to stick with our original plan here with a rational function. Not that this is always true, but really I would say it's more of a suspecting that the denominator might be a good candidate, right? So take a look at this one. Right, du here now would be 1 plus cosine of 2x times 2. So 2 cosine of 2x. Now, you think about that. You look at that and you compare that. Don't forget that dx there. You compare that to what you see up here, and it really doesn't look the same. And that's because there's kind of something that I don't want to say we missed it, but we didn't really pay attention to it early on. Let's come over here for a second, right? This top can actually be factored. You could take a 3 out, and you would be left with 2 cosine of 2x plus 1. Well, look at that. No coincidence that right there is du just tripled. But that 3, which is in the original problem, again, can serve as a constant. So I could actually write this integral. Watch this. 3, and then up top I can write it as 2 cosine of 2x plus 1. And then in the bottom, just keep the same thing I have, right? So when I go to set up my u substitution, the thing you want to catch here is that this is du. And I'm not off by any constants at all. And that 3 just kind of hangs out. So my setup would be such that it would be 3 times 1 over u, du. So it actually comes way back to something simpler. So our final answer here is going to be 3 ln of the absolute value of x plus sine of 2x plus c. So I wanted to just make you aware of that kind of thing because it might be under your nose the whole time and you didn't even realize it. Okay, your job. Let's try examples 3 and 4. Got the answers coming on the next slide, so pause and then play when you're ready to roll. Okay, let's take a look. Example 3, example 4. Of course, we can't answer questions on the video right now, but in class we can definitely help you out. Okay. Example 6 and 7. If you haven't done these again, spoiler alert here, just pause the video, go back, try those out. 6 is really interesting because, and I have a note here, keep searching for u. Very difficult in this one to pick correctly the first time around, so don't be afraid to pick something, try it out, kind of recognize that it's not the right thing to pick until eventually you get to what you need. And then I threw example 7 in there because it involves the fundamental theorem, so we can actually evaluate this integral with the area and go from 0 to 3. So we're looking for you to do that. You can do it by hand, but I did give you the decimal equivalent just in case. And then I'm going to finish up here with example 8 because what I'm trying to do is show you the importance of the absolute value. A lot of times people do enough of these problems or they try some examples and they kind of just glance over the idea that absolute value needs to be a part of it. And I'm going to show you exactly why you need to do absolute value here. So we do have a little bit of a u substitution. So u equals 2 minus x. du is off by a negative 1. Okay, so really we have negative 1 times the integral from 3 to 8 of 1 over u. Okay, so where does that leave me? Negative 1 ln of the absolute value of 2 minus x, right? And in this particular instance, we are going to be going and evaluating this from 3 to 8. Now, for a moment, imagine that you did not have absolute value around that, and you go to plug in 8, substitute 8 in. You're going to have an issue, because the ln of negative 6 can't be done. And likewise with 3, ln of negative 1 can't be done. So that right there shows you why this absolute value is so important. And let's finish it up. Because your answer now is going to be ln of the absolute value of 2 minus 8, so ln of the absolute value, negative 6, minus ln of the absolute value of what winds up being negative 1, right? Now when I go to simplify this and just kind of clean up, it's really negative 1 times ln of 6 minus ln of 1. And ln of 1 is 0, so really my answer is negative ln of 6. And what that should imply to us is that if we're finding the area really between this curve and the x-axis, if it's negative, either all of it's below the x-axis or more of it is below than above.